Gearon. I'm an engineer at RDoc. It's an organization that does enterprise architecture software, but that's not the topic of today. I'm going to be talking about a system that I built a couple of years ago now, which got integrated into ClojureScript as the math library. So, hang on, one thing that's been bothering me here, if I can pause. Great. So a long time ago, in a Slack space far, far away, Alex Miller announced new features and updates that were going to be in Clojure 1.11, including clojure.java.math. Now, that's a great development because it's inconvenient to use interop for many common operations like mathematics, but it's also very specific to the JVM. And when you're writing cross-platform Clojure, it could be very frustrating to be writing conditional compilation for like really common operations. I had recently ported a database from Clojure into ClojureScript, and I was running into this sort of thing all the time. Having done that once, I tried to make many of my libraries cross-compile where possible. And this sort of thing where we're seeing a library which is going to be different on every platform, where it could potentially be the same, was a source of frustration for me. So I asked Alex about it. And yeah, you know, a lot of the more complex math operations like sine or tan, logarithms, these sorts of things, they have a lot of overlap between JS math and Java Lang math. Alex said that he'd be cautious about that because there are certain numerical guarantees to these functions. And also, Java math has a lot more functions than JavaScript math. Now, they hadn't really considered, in the Clojure core team, they hadn't really considered that because portability hadn't been one of their goals, but it was for me. So, you know, what would be needed? How close is JavaScript math to what we need? Well, if we look in JavaScript math, we've got just a couple of constants, a few constants. Java math only had two. It's got a new one, tau, which if you haven't heard about that, then I recommend reading the Tau Manifesto. But the constants that we needed, E and pi, are both there, as well as several others. What about the functions then? Well, JavaScript math has quite a lot of math functions in there. That looked promising. How does this compare to the Java Lang math functions? Okay, so there's a few more here. Then again, the source code for all of this is generally available. It's in GPL, which means that you can't just lift it and move it. But where did that source code come from? Turns out it comes from things with much looser licenses. And so based on that, probably be able to re-implement a lot of these functions in the JavaScript space. But what about those guarantees that Alex was talking about? So let's see. It turns out that all JavaScript numbers are floating point numbers. Yes, even the integers. But most importantly, JavaScript uses the IEEE 754 standard for 64-bit floating point numbers. The standard covers a couple of different sizes of floating point numbers, but they stick just to 64-bit. But that's also exactly what Java does for its doubles. So that was a really good sign. There was one caveat though. The Mozilla Developer Network, they try to provide a definitive set of documents for the JavaScript ecosystem. And they make the point that there can be variations between different implementations. However, I went in and started investigating with some help from other people on Slack what might be involved in some of those other implementations. And this caveat is more about covering your bases than there being significant differences. Okay, so I could look up those details on Wikipedia as to what the 754 standard might be, or you could just buy it for $106. $83 if you're a member of IEEE, which I am. So I've got myself a copy of the standard. You can talk to me if you ever want to see it. And so I got back to him and said, look, it's using the standard format for numbers, missing a few functions, but I think I can do most of it. Let's see, I commented the source code for the bit manipulations available in JVM. For instance, the IEEEremainder function, I had started rewriting them and found that, it seemed to be working. And so Alex gave me the idea that maybe he was willing to hold off for a bit until I could go further in my investigations. Okay, so what's involved in these numbers? So the 64-bit floating point number format essentially represents numbers in scientific notation, except in binary. So you can see some constants on the left there. These are like the gravitational constant is first. They're all physics and math constants up there. Each is expressed as a decimal number, which is greater than 1, so 1 point something, and less than 10. So it's always a single digit before the decimal point. That number is called the mantissa. And then there's an exponential of 10, and that basically says where that decimal point will move to. Will it go to the right or to the left if it's negative? How many places will it move? Well, the IEEE standard does the same thing, except with binary. Now we have a mantissa that's greater than 1 and less than 2, and an exponential of 2, which shows the final placement of now it's called a binary point. But you see how that first digit has to always be a 1? It can't ever be 0? Well, they figured that they could get an extra bit for free because it's always going to be 1. Why bother storing it? So the standard, if you ever try to pull these numbers apart, that first digit is normally always missing. There are occasions where it's not, and we'll talk about that in a moment. So the general structure, 64 bits. We have a sign bit up on the far left, 0 for positive, 1 for negative. We have an 11-bit exponential. That number is actually biased. So if you see, it doesn't start at 0, that has a special meaning. If you see 1 in there, that is the smallest exponential you can get, and it indicates negative 1023. And then it goes up monotonically as any binary number all the way up to 2046. And then all ones has a special meaning as well. But halfway in between there, that indicates 0. So, the lowest number, if you see a 1 in there, that's going to be 2 to the negative 1023. If you see a 1023 in there, that means you're multiplying by 2 to the power of 0, which means 1. And the largest you can get in there is 1023. Okay, so that's the basic structure. And then the mantissa is just the decimal number that I was talking about. It's always shifted onto the left. So as with decimal numbers, once you've reached the number of decimal places accuracy you have, it just runs off to zeros on the end. So there are special groups in here. If we start with an exponential, which is all zeros, if we have everything at all zeros, except the sign bit, which could still be 1 or 0, that is 0. If the sign bit is set, that means negative 0, and some of you may have seen negative zeros in with the software that you've worked with, if it's floating point. If the exponential is all 1s, that means infinity. Again, we've got positive and negative. However, the mantissa has to be all zeros. As soon as a single bit in the mantissa is not a 0, then instead of it representing infinity, now it represents not a number. You'll notice we've got, with the exception of that, that first mantissa bit, we've got 51 bits, of which any one of them can be 1 and will have a not a number value. There are actually systems out there which will encode errors into their not a numbers. If you're going to throw a nan, then this is what this first bit can represent. It can indicate that we want to signal that there's an error here, as opposed to let's just pass a not a number back. So 0 divided by 0, you might allow that through your system, but if you turn the signal on, no, that's got to be thrown as an exception. And then finally, and the one that's most of interest to me through the coming slides, is the subnormal numbers. Like 0, our exponential is going to start at zeros, but then the rest of the number is in the mantissa. This indicates that our numbers are less than 2 to the negative 1022. Now, these indicate very, very small numbers, and at this point, we're going to presume that they are not preceded by a leading 1. Now, it's like a 0 point, and this is our number. And this allows us to get smaller and smaller numbers, because we can start with a leading string of zeros. We can get smaller and smaller numbers all the way down to the very tiniest numbers that can be represented with this format. And it's by not having this 1 on the front, we're treating them a little bit differently. This group of numbers are referred to as the subnormal numbers. And yeah, they cause all sorts of grief. So how might that look? Well, let's consider this number, 12,345. It's got this binary representation up here. It's positive, so first bit is 0. Turning it into scientific notation just means adding a point after that first digit, and the exponential is just going to say how many remaining binary digits we have. Now we're going to throw away that 1, and that's the number we want to write into the mantissa. The rest of it will be filled with zeros. Then it's 2 to the 13 that it's multiplied by, so that gets put into the exponential, but we first have to add the bias. So we get 1036, it's that bit pattern, so it goes into the exponential. That's how any number gets represented internally in both Java and JavaScript. Because JavaScript uses integers, we're also going to have, it doesn't use integers, it pretends it uses integers. What it does is it uses the mantissa to represent that. So we can go up to the 52. And that gives us our range of integers that we can work in. Of course, the exponent is going to say how many bits of this that we're actually using. So there's still normal floating point numbers, except the exponent is only going to take us up to a point after which there'll be all zeros from there on. But this structure is what leads to the maximum safe int and the minimum safe int in JavaScript. If you try to go any higher or any lower, then the decimal point, the exponent has to go up 1, and there's no extra digits that we can put on the back, and so we're going to lose those last bits of information. And if you try incrementing up past the maximum, for instance, you'll suddenly see that you're jumping by 2, and then you'll start jumping by 4s, and then you'll jump by 8s, and that's as the exponent continues to go up, and we don't have the bits to represent the integer values anymore. And that's why these are called the safe integer space, and anything outside of that, we can round off, but we don't have accuracy anymore. So how can we do bit manipulation like this in JavaScript? I mean, I came from C, I know how to do it there. Well, to work on it, we'll want to slice out the high and the low double words, or 32-bit slices. We might also want to work on the 8 individual bytes that make it up. Now, when we're using little endian systems, as we often are, then these get counted from the least significant to the most. To do that in JavaScript, I'll talk about this in a minute, but it was very difficult to do until we started getting array buffers. So using this interface, what we can do is allocate an array, in this case 8 bytes to hold the double, and then we can put a facade over that buffer that looks like an array of 64-bit floats and another array of 32-bit ints. Now, the 64-bit floats, because there's only 8 bytes there, we're going to have a single entry in that array. And in the unsigned int 32 array, we've got 8 bytes, so we've got 2 of those. Now, we may be on a big endian system, so we ask this flag of little endian, are you set or not? And we're going to set this high value to 1 or 0 based on that. And that flag we can calculate by simply putting data into such a buffer like this, and then looking to see where it ended up. Okay, so now I've got the where the high flag is pointing to, 1 or 0. I can now take my double, put it into the float 64 array in position 0 there, and now I can get out of the integer array both the high and 1 minus high to get the high and the low double words. Now, on Slack, Mike Fikes expressed some concerns about that mechanism because it's not supported on older browsers. David Nolan was wondering about it as well, and we ended up having a long conversation and trying to figure out if we could effectively do it another way. Is there some other way to get to to some of the bits? We can definitely get to some of them, but there's no effective way to pull all of them out with other sorts of operations. This is the only way we figured we could do it. And it has been around for a little while now, and so in the end, David agreed that there's no other good way to do this, and it was acceptable. Okay, so once we have these high and low words, we can use typical operators to do bit manipulation. Sounds great, except we're supposed to work on integers, but JavaScript has floating point numbers. So how does that work? Well, it turns out that JavaScript implicitly converts the number into a 32-bit value. Anything larger than those 32 bits is just thrown away. So what's that look like? Well, let's say I do an OR with 0. That should give me back my same number, right? And for a number that stays within 31 bits, that's what I see. But if I use that top 32nd bit, suddenly the number isn't the same, it's negative. And that's because all numbers in JavaScript are signed. Well, let's say I go for an even bigger number, and now it's, I don't have that top bit set on for this particular number, but I do find that it's truncated the higher bits. So I've got sign flipping going on, I've got truncation going on. It's a little bit messy. But at least we know what we're looking for here. So let's go into the implementation. A lot of the functions that we want to work with don't have to worry about this. We can just use simple wrappers. And in fact, the Clojure Java math was doing exactly this. So I mostly copied these functions out, changed the documentation, removed the inline operations that Clojure Math now has in it. Just made it a simple wrapper around the JavaScript operations. And this is the Java version, but it ends up being almost the same in JavaScript. Actually, no, sorry, this is the JavaScript version. Other functions needed a little more work to make it work just like Java, mostly bounce checking. So for instance, if we're doing a rounding, according to the Java documentation, if you have not a number value come in, you're supposed to return 0. That's not how JavaScript operated, so I dealt with that. Same thing with infinite numbers. I had to return either the max safe integer or the minimum safe integer, because these were the only things which are going to be appropriate in this case. And the default case, I just get to call round on it. Again, more operations which didn't seem too hard. This is getting to the point now where I don't have functions in JavaScript, but I can re-implement them myself. So this is for division. Not too hard. We have to do a little bit of work pulling out elements of the properties on the various numbers, and once we know that they meet certain criteria, we can look for the bounds, ranges of them. Is one of them negative? Is one of them positive? Which way does rounding go? That kind of thing. We can implement this ourselves and return it. It's relatively straightforward. I got through pretty much all of these functions in the first couple of days, and thinking I'm on a roll, it's going to be done really quickly. Then I got to some trickier ones. The unit in last place function. This one, we're now really pulling apart the bits. We're really looking into what's going in. I'm checking up some of the other reference implementations of this to make sure that I've got it right. But generally, it's working out well. Again, with all of these re-implementations, took a day or two for that. So I'm on a roll, I'm just about done, and then I hit IEEEremainder. And it was kind of complex. It operates the same as mod, except it offers extraordinary accuracy for very small differences, very small numbers. And like looking at the implementation, it's a lot. I asked, do I really need this? I mean, how many people really need that level of accuracy? But I promised. Okay, so where did it come from? Originally, FDlibM came from Sunsoft, Sun Microsystems. It was a part of Sun Microsystems. It came out in 1993. It's currently hosted at the NetLib Math Repository at University of Tennessee, Knoxville, and the Oak Ridge National Labs. So NetLib is co-hosted by them. It has a BSD-style attribution license. So looking at that, it gave me a lot of confidence that I wasn't going to be violating any licenses if I went and started looking at how different people had done this, because everyone had built their code over the top of that. We find this code also in glibc, and we find this code in the JDK. Now, when I looked at this, at the time, it was in this path, ending with E_remainder. March of last year, they moved it into Java code. And in fact, they've been doing this ongoing movement of native code into Java code starting in 2015 for the whole math library. So everything in math will eventually end up there. But IEEEremainder got there in March of last year. Hadn't when I did this stuff, so I'm looking at it all, how do I do this in JavaScript? So looking into it, this is the C code which implements it. Oh, no, not. This is a very small slice of the C code that implements it. It uses a function called fmod, floating point modulos, and this is a slice out of fmod that we can see here. There's comments there saying that it's determining the integer log binary values for x, doing various operations in Yeah, and it kind of looked like it was duplicating things here, and it was really expanding the size of the function. I figured it was probably appropriate to pull out into its own. So in ClojureScript, it looks like this. This is essentially a transliteration. Going back into IEEEremainder, again, we're looking at some complex code here. Lots of bit shifting, negations going on, this sort of thing happening in here. But see these comparisons? This is the low x, is it less than the low y? And also down the bottom, same deal. We're going to be doing this decrement on HZ, if that's, oh, HZ, I'm in America, sorry. And we're going to be doing the decrement if that's the case. I totally didn't see this at the time. Just remember them for a moment. So I implemented it in ClojureScript, and it looked great. I put numbers through it, and I was getting exactly the same results out. Wonderful. So then I started running some more testing on it, and everything looked fine until I put a number in and I got something completely different come out. This took a lot of debugging, and I ended up doing pulling apart glibc, rewriting fmod, and putting print statements in there to see what it's getting out and comparing it to what I'm getting out, and all sorts of things happening in here. And it turned out that it was these less than comparisons. You'll notice that I have u less than because I had to re-implement that for myself, and it's these lower order double words, they're being turned into signed values. And so I compare the top nibble before I then go on to compare the remainder. You know, little gotchas like this were catching me out at all sorts of turns. But, you know, this was my final function. It was my white whale. I took a couple of days on it, but I got it out. It felt amazing. So finally, it's all running. So I'm done, right? Well, I need to test. And it had to be rigorous. Like, people rely on math. You can't just wing it. So the first step was to run it all on the JVM, because, I mean, this is JVM compatible code. It's Clojure, so it should just work, right? And I could even compare those results directly to Java-lang math. Even better, I could use generative testing to compare the results of my libraries to Java-lang math. And, you know, that way I can't hide any indiscretions. But of course, some of the code doesn't just work. I was making references to several JS entities. So let's address those. I stubbed it out in a namespace that I called, naturally enough, JS. I put in the various safe integer ranges, positive infinity, you know, things like this. Functions like isNan, isFinite, isInteger, which I had to call. They're now in Clojure proper, but they weren't at the time. Let's see, is safe integer. But what about those buffers that I was using for moving this data around? They look an awful lot like the NIO buffers that we have in Java. So, generated a couple of classes to represent them, and created a protocol of array access to get them, using an aget and aset operation, because that's how we were using arrays in ClojureScript. So using that, we can do some constructors up the top there, where we just create a buffer, or we use asInt buffer, as double buffer, which is all NIO operations, and then extend the protocol onto these classes now, and we handle the signed elements. Like, you can't put negative numbers in certain places. You know, we're looking for unsigned values that we want to work with here, especially for the uint8 and the uint32s. Okay, so now we can do generative testing. That first line there, d equals, that was a function I had to write because sometimes a function would come back with nan, and my function would come back with nan, and they're equal, right? Except nan is never equal to nan. So d equals is a double equals, and it considers that as well. Safe integer is a range of integers that that we can operate across when doing generative testing, just going from the minimum to the maximum number. We don't want to go out of that range because otherwise things get rounded off and it's not going to work for us. And I can do things like, here's a sine test, here's a cosine test. Very easy. I just say for all doubles, and the math cos is equal to the Java math cos. And these things worked. It went great. More functions looking like this, and this actually was how I was testing IEEEremainder. I thought I had it working, I didn't. I got it going again. I thought I had it working, I didn't. I got it going again. And this was really the pass that got me really happy. In my notes here I've written, I was giddy. But there are some problems. This calling Java lang math, using the floor mod operation from 1 with this enormous number, generative testing through this number at it, it's supposed to come back with 1, but it doesn't. It returns this instead. I asked in Clojurians, and people started coming back, like Adrian Smith immediately confirmed what I was seeing. He pointed out, yes, this occurs on various JVMs even. What's going on? Well, it turns out that the reflection code picks up the wrong method overload, and it casts that second number into a 32-bit int. Now, that ends up being easy to work around just by casting, but it's a good reminder, actually, that I wasn't being careful about reflection. So we do, unfortunately, still see this in Clojure today. This bit of code here will print whenever it gets a bad result. And these are the errors we get. However, if we cast it, nothing comes out. So this is actually one of the reasons why Clojure Math is a good idea, since it'll actually ensure that people aren't accidentally reflecting. Okay, Alex checked in with me about that time. I was happy to assure him it looked good. Now I needed to get it into the ClojureScript proper. So shouldn't be hard, everything runs, right? Mike Fikes gets back to me and says, some comments. He'd been following along, he had a look at it. After the highs of that IEEEremainder success, this kind of brought me back to earth. But these suggestions are actually mostly about performance, and they were all excellent suggestions. And he was more than happy to help me out at every step. He knew a lot more about the ClojureScript system than I'd ever considered. He had lots of tips and tricks and things which I could pursue to improve what I was doing. A simple one was this one. If you set print function bodies to be true, and then you define a function, then when you evaluate that function, it'll print the JavaScript that was generated for it. And so you can get immediate feedback. What if I encode it this way versus that way? You can see how this is going to look right there in your REPL. I can't tell you how much I appreciated Mike's help during this period. It was, the things that he was suggesting to me were really valuable, and I really upskilled on ClojureScript during this time. So on December 10, a couple of weeks after initially starting out on this, I was feeling confident enough that I made a formal request on Slack about how to include it in ClojureScript. It turns out that most of how to include it is documented. Here I am reading formal specs and forgetting to look in obvious places like javascript.org. But it did inform people what I was doing. So a lot more people started looking at it at this point. Okay, so now we want to get it into JavaScript. Can the generative testing that I was doing earlier, can that actually compare the JVM output to the JavaScript output? Because that would be, ideally what I was looking for. So how could I do that? Well, step one would be to create an nREPL in the JVM, but you can only really talk to that through strings. So let's do the generative testing using strings. I'm going to start out, I've got a new equality function here. I'm looking for is not a number. Now I'm actually looking to make sure that things are numbers, because sometimes they come through as strings, etc. Or I could get an error, an INF or something that the reader doesn't like. Are they both the same thing coming back and equal, or are they just equal? So now I can do my exponent test. I'm going to do the sample, ds being a sequence of double values, and then I can map my ClojureScript get exponent over them and map my Clojure's get exponent over them. And then if I map equality down those two sequences, is every identity will tell me if anything's false. But that bit, CLJS get exponent, how do I get that to work? Mikkel Borkent happened to be looking online, and I was saying, yeah, I'm thinking of setting this up. A couple of minutes later, he posts this. I was talking about maybe using a pipe, he's used a socket, but you know, I'm not going to complain about working code that I don't have to write. So now that I've got this, if I put some code into it, does it work? It does. I can eval this expression, and sure enough, I get back out the answer. Okay, now we can generate the samples for generative testing, print it to a string, the string expression that we want to read and evaluate, and compare those results to running the same JVM function over the sequence. So the two sequences are then getting compared with the equality operator and checked. So you can see in my, up here, it's putting that sequence right in the middle. Now, that string, you know, making it look a little bit messy, but it effectively ends up looking like that, where we've got the sequence now embedded into our string. Now I've got square brackets there. Oftentimes when you're generating a sequence, it's going to be a list, so it'll be round parentheses, hence the need for the quote. Okay, so this is working, but it's going to be very tedious to set up over and over again for all the functions that I wanted to do it on. So how might we make this a little easier to do at scale across all the functions we need? Well, what about macros? Focus can explain why I can't tell you about macros, but this is the basic structure. This macro runs on functions that take a single argument of a type, hence the test T, and it returns a type, so that's why it's T to T. So the type might be a double, or it could be an integer. Now the first thing the generated code does is generate that sample. It then does what we were looking at earlier, where we emit the numbers, convert to doubles, then we map the expressions of interest over them. And so you'll see the CMFN was the ClojureScript function that we want to map over it. That's just getting spliced in. We're going to do the same mapping over the sequence in Java. And finally, we compare it all. So now that we've got that, we can start expanding it out, and now we can start building more macros over it. So like test double to double, or test function that takes two doubles and returns a double. And we build this over the previous macros that we have. And so there's a few different variations in there now. I'm not showing them all. So then we get to write nice, simple expressions like this, and it executes equivalent operations on the JVM and a ClojureScript REPL. And there's several variants here, including comparisons that can print what's going on when values are close but not equal, or operations that can't take zeros for some arguments, like the floor div, you can't divide by zero, that sort of thing. And so with all of that going, now I'm feeling more confident. So I explained everything to David. We had a number of conversations. He approved. And David's standards are so high that getting something approved by him was almost as good as getting IEEEremainder to work. So I learned how to follow the formal patch process. It's on the website if anyone wants to do this. A created an appropriate Jira ticket, attached the patch. Then David said he'd merged it. And a handful of people said they liked me. So then we had to wait. He hadn't made the next release yet, and I was getting impatient. But if you recall, in Alex's original announcement, there are a whole lot of new functions coming out, and they weren't in ClojureScript yet. So I went and did those, because what else am I going to do while I'm waiting? And then it got released. This was about 6 months after I started the process. Some of that was just waiting. Some of that was getting feedback from people. The original tough part of the coding literally took 5 days. 95% of the work was not the coding. It was working with the people involved. It was going through the community process. It was making friends and having people help me at every step of the way, learning how to integrate in with the larger ecosystem. It's somewhat belated, but I want to say a special thank you to everyone who helped me to get it done. Alex Miller for being willing to hear me out and changing the name from clojure.java.math to clojure.math. Mike Fikes for his friendship and thorough evaluations, along with patient and knowledgeable explanations. David Nolan for his advice and willingness to work on this with me. Mikkel Borkent for saving me a couple of days of work when I really needed it. And everybody who interacted with me over Slack with comments, suggestions, or encouragement for what I was doing. It helps motivate you when the community likes to see what you're doing. And so I just want to say thank you to all you out there.